I would like to welcome everybody at the second session of the day devoted to atomic BECs. And the first speaker is Giacomo Roati from Lens. The floor is yours.
Everyone, first of all, I would like to thank the organizer for the great opportunity to be here. My first time in India, and of course, first time in this very nice place. And I'm very looking forward for listening to your seminar because, of course, the topic is very relevant for the activity that we are running in Florence. And so also to have other point of view is fundamental. So as said, I'm going to talk about some experiment that, in fact, we run on Fermi superfluids with lithium atoms. But you will see that, in fact, the specific nature of the fermionic will enter only in some part of the presentation. Okay, this does not work anymore. I don't know why. Okay. So this is the team that we have, that I'm very happy to lead. This is Giulia Del Pace, Nicola Grani, this is a young student, Giulio, and this is the senior PhD, Diego. And as said, the activity is run in Lens in Florence. Okay, so why we decided, in fact, to enter and to study vortex dynamics? Well, because in general, there is still quite a lot to be understood, and this can be, of course, connected to the difficulty in describing vortex and vortex dynamics in general, due to the interaction between vortices and the medium, vortex-vortex interaction, and as said also in the previous presentation, due to impurity or material disorder in general. What is known is that anyway, typically, the vortex, and in fact, the vortex motion in superfluid and superconductor is associated to dissipative mechanism that can be described in a general term by phase leakage event. And okay, these are two examples that I got from two papers in superfluid by the group of in Berkeley, and this is the group. A theoretic paper describing the transition between a superconductor and insulator driven by disorder. Okay, so this is a very similar slide that was shown before by Andrew. For sure, vortices are present in both classical and quantum system. And the difference, or one of the differences that I want to point out, I don't know if it is the main one, is that if you define a circulation, of course, in case of classical system, this can assume any value, while, as said before, the circulation, should be quantized in case of quantum system. Oh, sorry, now this will work again. Okay, sorry. Okay, so one topic that we want to cover in Florence is what about dissipative mechanism in vortex dynamics? Of course, in the case of classical system, we know that the vortex can lose in some way energy through viscosity, and because typically viscosity is present in normal fluids. While, of course, if I go to study system like quantum vortices, and in particular, okay, this is an example taken by MIT work in the case of ultra-cold gases, then how vortex or quantum vortex, if you want, vortices can lose energy, the swirling flow energy, in systems that are typically without any viscosity. Okay, so I tell you, typically we can distinguish two different regimes. And one regime, of course, is the one in which the system is at finite temperature. And we can speculate that the interaction between vortices and non-condensed part, or normal fraction, of course, can give a way for the vortex swirling flow to decay. And this is called like a mutual friction. This I will see is encoded in the mutual friction coefficient that are typically phenomenologically introduced to describe this event. Oh, sorry, this is super sensitive. Sorry, I will probably go. And in fact, this is what happened, and I will not enter too much in the detail, okay, because probably the audience is more expert than me about this. But people like to introduce two kinds of force, of course, the Magnus force and the mutual friction force. And in particular, for the mutual friction part, you have two kinds of coefficients that are longitudinal and transverse that describe simply the way in which vortex can interact with the quasi-particle in the medium, okay, or normal fraction. And these are connected then to two coefficients that typically are the one that people measure or extract in the experiment, and this is what we also do, that are called alpha, alpha prime. Okay, this depends, of course, on many quantities, but the circulation, the superfluid density, and I mean, these are, I will not enter again into much in the detail on this. And of course, at the equilibrium, these two forces must balance. Well, then, of course, what happens is that if I reduce temperature, you can expect that the normal component decrease, and then you expect that eventually vortex are completely, I mean, there is no way for the vortices to lose this Whirling flow energy. But this is not the case, because typically these systems are compressible, and so it is possible that vortex swirling flow can decay mixing with or with other degree of freedom of the system that, for example, are compression mode, like phonons. And this, okay, is an experiment carried out in helium-4. So without entering too much in the detail, if this Y scale you can consider like an effective viscosity, okay, versus temperature. And you see that, in fact, even when you reduce the temperature much lower than the critical temperature, this value, in fact, seems to saturate to a value that is not zero, okay? So it seems that, like if vortex, also in the case of helium-4, at approaching the zero temperature limit anyway, still have a way to decay. So just as a summary, very, very qualitative, but just to give you the message. So we can expect that at finite temperature, mutual friction coefficient, and in fact, is the scattering between normal components and vortex, can create a dissipative mechanism. At zero temperature, eventually, this can be also true through the scattering, or the combination between vortex and sound, if you want to say. This could be a way in which the vortex can lose Whirling flow. Okay, then comes the point that, in fact, the situation is more complicated than that. Because in the case of, in particular in the case of fermionic system, what I recently learned in a conference in San Feliu by Sandy Fetter, that this can be also valid in the case of bosonic system. So we are considering the system composed by vortex that has a density that drops the superfluid order parameter going to zero completely in the vortex core. But this is not always the case, even for bosonic system. We can simulate this, for example, in two species BC, or just adding finite temperature system, okay? This means that, in principle, I will call quasi-particle, but can be whatever you want. Quasi-particle can fill up the vortex core. And this is, in fact, a process that is very well known in the case of superconductors and in Fermi superfluids in general, because as found by Dejean and Caroli and Matricone in the 60s, in fact, in the BCS superconductor, the vortex core are not depleted. So in fact, exists really a bunch of bound state that are called under-bound state, and quasi-particle can be really populating this bound state. So this means that for fermionic system in particular, but okay, Sandy said also for bosonic, but let's be for sure there is the theory for the fermionic is very well demonstrated. This can give us as an additional mechanism, because quasi-particle inside the vortex core can scatter with quasi-particle outside the vortex core, and then create an additional way to make another mechanism to have the vortex energy to decay. Okay, and this, in fact, is more or less what has been observed in the case of helium, and without too much entering the detail. So they extract in experiment D and D1 and D prime, that is, in fact, alpha, alpha prime, for helium-4 and for helium-3, and here, this is the case of helium-3, they really can extract information about this mutual friction coefficient, and you can see these are the data versus temperature for the coefficient, and this line is the continuous line is in fact the theory that include under-bound state scattering. So the system in fact behaves like this. Well, now why we study this? Because we have a special superfluid, in fact, I mean, not only, of course, in Florence, but there are many other places in the world, that is the unitary Fermi system. And for the unitary Fermi system is a little bit more complicated, or maybe more interesting if you want, because these are generally speaking, very strongly interacting system, and then very strongly correlated. And then if I go just to see the mean free path, for example, of quasi-particle, or the vortex core size, has the scale with the inverse of the density, so 1 over kf, you see that they scale exactly more or less with in the same way. So in some way, we have a system for which vortex core size is the same size of the mean interparticle spacing, that is also the means of the same size of the mean free path of the particle. So the diffusion coefficient for sound, for example, or for in general, is spin, for example, is limited by quantum mechanics to h bar over m. Is the minimum possible in nature due to the resonance scattering that you have in this system. And this is a calculation in which people started to extract the 100 bound state for our system, or for unitary Fermi gas. And this is the vortex core, if you want density, moving, increasing temperature. And you see that anyway, there is an increase of the population of 100 state in the unitary gas. So you can expect some effect even in the vortex dynamics. Okay, so on the other side, and this, okay, again, the audience here is much more expert than me. Vortex dynamics is associated to fluid instability. And okay, there are many examples. I will probably touch a little bit about the Kelvin helmets, since also there is Andrew here. That would be nice to discuss, and Iacopo as well, because in principle we can think to do some experiment on this. And of course, this is strongly related to quantum turbulence. And again, here we have people coming from the group of Zoran. So unfortunately, it's missing near here, but this the topic of fluid dynamics and fluid motion and instability is strongly connected, of course, naturally with turbulence. And I want to stress also that the fact that one can study vortex sound instability is also very important, because this is a way which vortex in a turbulent state can decay, okay, typically. Okay, so this system is very complicated, probably as my introduction, and this is why we decided to work and to study this kind of system. Okay, that's, I don't know what I did, but I will solve the problem very soon. Okay. Okay, so, of course, we are not the first, and we are not the last studying vortex dynamics in a system, in atomic system. This are just some experiment in which vortex appear. So you can go from MIT to ENS to, again, MIT fermions and GLA experiment. But of course, there are many, many other experiments that are running on vortex dynamics. So what we wanted to do, we wanted to use a bottom-up approach and taking advantage of the possibility that I think is unique on cold gases to control and manipulate the system almost with very easily. And so this means that we want to add one vortex by one vortex, and we want to track, eventually track vortex trajectory in a very continuous way. And okay, this will be an example that you will see. These are two vortex dipole colliding, okay, one against the other. Okay, this is what we can do in the experiment now. And if you want, this is a more arrogant, if you want, but this is just to give you also the idea. You know, people now are working with atom in the Rydberg, with Rydberg atom in a tweezer, optical tweezer, and they can really start to move one atom individually. So our idea is to do the same. In fact, we use tweezer to do this, so it's the same, but with vortex matter. For example, you see here there are three vortex dipoles that are going to interact against each other. So you can see this black dot in the density that are the vortex dipole. Okay, so how do we do this? First thing, we need an homogeneous gas, because vortices and vortex motion is very sensitive to this homogeneity, okay? So this is our Fermi superfluid, but can be also molecular BC, so just to people that are scared about fermions, we can do also bosons. But more or less, we don't care because it's another parameter, except for the 100 state that makes a difference. And we can control temperature, and so the system is 3D, but quite oblate, but vortex dynamics is 2D. Okay, so we really have probably actually only the first Kelvin mode populated, so we don't have, it's super thin, so the line cannot bend too much. Okay, so we can treat the vortex like 2D system, 2D particle if you want. And then we don't enter too much in the detail, but we have full control of temperature. So we can do with the equation of state for unitary Fermi gas. This is very nice because we have all the tools to extract T over Tf, then T over Tc. Okay, and this is what we do. We took MIT equation of state and we apply the Henning-Moritz group way to extract temperature in the system. So, but you have to trust me, this is what we can do easily. Wow. I think this most, so what we do, the second ingredient is that we need to have a high numerical aperture and to have a microscope objective, because we want to see the atoms and we want to imprint a potential with very high sensitivity and very high spatial resolution. And so this is typically, this is our gas and this is the objective coming from below. And then we have the third ingredient that is the DMD. So in principle, it's the same thing that you have in this projector. We have a device that allows us to imprint any kind of potential of our atoms. So this means that we can imprint any shape with the maximum resolution possible. And these, for example, are different. Okay, this is a heart, you can see very well. We have ring, and this maybe if I have time or otherwise during the week we can discuss. We can imprint ring, so with this a superfluid ring. Then we can have a Josephson junction necklace, this is another experiment. Or we can also control the potential dynamical, so we can really move the particle around the system. Or if you want to have some more fun, we can also create very funny, and this is now, it's more Christmas, but this is just to give you the idea of what we can do in the system. So meaning that we can, and the resolution that we access is below micron. And the mean interparticle spacing is below micron, so this is 1 micron, and vortex core size is around 1 micron. So it means that we can imprint potential on the same scale that we need, okay, to really be very sensitive on the scale of the atomic system. So I don't think that I will have any time, but we did 2 experiments that probably can be relevant for this community. One experiment is to study vortex dissipation in Fermi superfluid by studying vortex dipole propagation or planetary motion. And then we did, in fact, an experiment, Andrew here proposed, using 2 rings and 2 counterflow superfluid to study something that I like to call Kelvin-Helmholtz instability or superfluid Kelvin-Helmholtz. People can also tell that is vortex lattice instability. Anyway, it's driven by some fluid instability that is behind this system. Okay, so how do we produce the vortex? And this is very simple for us. I was discussing with Alessandra 2 days ago. So in fact, it's very obvious what we do. We take a superfluid, and this is blue part, that is also this one. And then we take 2 atomic tweezers, so 2 repelling barrier, and at 0 time, they are completely superimposed. And then at time 0, we start to move in the superfluid like this. Okay, 2 defects moving with some velocity in the superfluid with an angle. And after some moment, we switch off this tweezer or this pinning potential, like just to use the same nomenclature of before. And then what we have is a vortex dipole. Okay, we do not transfer any angular momentum. So the only way in which this can be at the end is 1 plus 1 minus vortex. And of course, if we I think that what is important, if we overcome a critical velocity, that is some fraction of the bulk, this is the bulk speed of sound, can be very close to the local speed of sound, then we can discuss around the defects. Anyway, we have 100% fidelity to create a vortex dipole. And this is very important because it means that every experiment I'll run, because then we have to switch off the system, take image, because it's destructive imaging. But then since we have 100% of probability to recreate the same vortex dipole, that means that the system is totally able not to perform simulation and to acquire data, reducing fluctuation. Okay, that I don't want to enter too much, but we can also see with the resolution, of course, vortex in situ. But for all the experiment that I'm telling you, we just switch off the trap, the atoms expand, and so the vortex increase size, of course. For lithium, is very light, but I mean, just to say that in principle, it is possible to get it anyway. So that, I don't know how much you can see on the screen, but you can see these 2 black points that are doing some very nice trajectory. So this is a vortex dipole. We release from the tweezer and they start to move. And you see the trajectory, okay? And they perform very nice trajectory because approaching the boundary, then of course they must be reflected. There is an imaginary vortex. So, I mean, the dynamics is very well described by Gross-Pitayevsky, but these are the experimental data. So why we wanted to study a vortex dipole and not a vortex? Well, because to extract information about dissipation, we need something. And the something that I need in this case is the size of the dipole, because the energy of a vortex dipole is logarithmically dependent from the size. So if I see a change in the size, means that something is happening to the vortex dipole. So in some sense, I would say is quite smart, because we cannot measure any frequency here, but the second thing that you can measure nicely in physics probably is the size. So measuring the size, we extract information about the energy that the system has. And this is why it's important that the vortex move in a flat landscape, okay? Because if I have some corrugation, then I can have some issue. So you have seen this. Okay, so then of course, once that we know what we have to measure, now we have to see what we can, which is the equation that we need to use to describe the trajectory. And again, this is we use the mutual friction coefficient and the Magnus force, and anyway, without entering too much in the detail, we have this equation for the velocity of the vortex. That in fact will depend on two coefficients, again, that is alpha prime, that are the two mutual friction coefficients. But I want to give you an intuition of what are these mutual friction and what is the physics behind. But again, you are the most expert here probably. So if I don't have any dissipation, and the vortex dipole is sufficiently large for which there is no annihilation, okay? So what happened that the vortex dipole propagates at infinite. Of course, I will have a wall, because my system is finite, but then we'll do this kind of half moon motion. But then suppose that I start to add the mutual friction coefficient alpha, okay? So this is still 0. Then what happens is that during the motion, the vortex of plus minus start to become closer and closer. And eventually, if the dissipation is such large, then it becomes so close that they annihilate. This is the idea. Well, then if I turn on, oh, sorry for this. Okay. If I turn on also the other coefficient, then in fact it's like to delay the motion. Okay, so it's like the center of mass motion is slowed down. Okay, so if I don't have alpha, the vortex will just be slowed down without approaching. If I have both, that is typically the case, then I have both the two vortex come to become closer and then eventually are slowed down. So these are the trajectory of the plus minus, whatever you want to call, vortices versus is an example. And what we use then is to fit this equation in the so-called framework of dissipative point vortex model that is using the equation of the velocity that I described just above. And then we can extract alpha and alpha prime. And this is an example for alpha. So I want to say that in this experiment, the previous one, we set alpha prime equal to 0. And this was an assumption also for typically people set this to 0. And in fact, we see that it's not, but it's not affecting still the alpha value that we found here. So that everything will be consistent. But anyway, this is alpha, and this parameter eventually is just the interaction parameter. So it means that if I go in this direction here, is the BC that you like a lot. If I go in this direction here, is what superconductor have, so is a BCS. If I have 0, is the strongest, is the unitary gas for which, again, the system is strongly correlated. And these lines, just before you ask, is a NIC theory that we are very happy works super fine in the BC limit. And this orange is a theory that is more complicated for me to describe, but is something that is even not totally related to our system, but is a theory that we get from Thomas Gazenzer. Okay, it's this holographic theory, high temperature. But it's the only thing that we could compare at that time. But the message is this: if I move from BC to BCS, the dissipation increases. And in fact, the unitary gas is not behaving such bad with respect to the BC, but still is more dissipative. And the BCS, that are these points, is much stronger dissipative. Then we enter in some discussion why the BCS is more dissipative. Well, then we can enter in any, it's a hell. For sure, we can think that there is quasi-particle scattering. Maybe it's finite temperature, so we are not so good to reduce the temperature as we do in the other two regimes. Anyway, we are collaborating with Gabriel, and Piotr, and Andrea in Warsaw. And you will see in the last 5 minutes what I'm going to tell you about. And because they can run, and we can run with them, superfluid simulation with fermionic system. Okay, so at that moment of this paper, we did not have the possibility to compare. Well, then, always to go in the direction, too much time to describe, but what happens if I create two vortex dipoles and I let them crash one against the other? Okay, this is an example. Of course, how we produce, you will have plus, minus, minus, plus. This is for symmetry reason. And I want to tell here that this was a very nice collaboration with Galantucci, that is here, and with Cledia, that in fact could run simulation to extract the information that is very relevant for understanding. But anyway, you see here, this is just a trajectory, of the two vortex approach, the dipole approach, the plus pick up the minus of the other, and vice versa, and then do a sort of. So if everything is fine, you don't see, so if the vortex dipole are sufficiently large, you do not expect nothing. So it's like an elastic scattering. But then, of course, if you start to see that this size and this size that are the entrance channel are larger than this size and this size, means that during the interaction, something happened. I don't have time, but happens that dissipative mechanism still can arise, okay? Because of course, if the dipoles are not sufficiently large, you can have some exchange of energy in the system. And in fact, what we did, and this Luca and Claudia, we were super happy to see both in the theory, then that are the yellow for different angle of impact between the vortex dipole, and in the experiment, we see that if we prepare sufficiently small dipole and we let them crash, then after, okay, this you see better in the theory probably, you don't see anymore the dipole, but you see sound wave exiting from the collisional point. And you can see also probably, I don't know how much you can see here, but these are the dipole. You see this black ring here? This is the wave, the sound wave that is exiting, that is after the collision between vortex dipole. And this, of course, this is for, just to be clear, BC experiment, BC theory, but the same thing we can see in the case of Fermi superfluids. Well, just because my time is, I have 8 minutes, so for the Kelvin-Helmholtz we can discuss, but maybe I will show just one slide very fast. So we wanted to go more in the detail. So what is limiting our experiment now? The fact that the vortex move and then arrive to the finite size. So it's finished. My system is not infinite. Well, then the students were super smart and they said, okay, why don't we do another kind of experiment? And why we want to do this? Because we want to have probably information about also the alpha prime coefficient that we set to 0, like in most of the treatments so far in cold gases. And there is a big debate in the case of helium-3. I mean, I will not enter. There are many Russians that work on this, Pitaevsky, Jordansky, Kopnin, and so on. Also, I mean, there are many eminent persons. And the problem of this alpha prime coefficient is still under debate for Fermi system and could be due to the interaction between sound or quasi-particle and vortex. So anyway, what we do for the experiment to try to go there? Well, in fact, we use a pinning potential. So instead of depinning both the vortex, we keep one pinned. So the other one has to rotate around, okay, in a sort of planetary motion. So one vortex can be plus minus, for me it's not important, remain pinned and rotate, of course, around the pinning potential. And the other one has to do a orbit around. Why? I mean, which is the advantage? Of course, then it's simple because I constrain the vortex dynamics in the central part of the cloud. So they will not explore the border. Actually, we reduce as much as we can. We can follow more evolution because, of course, if they don't arrive to the end, they can rotate, I mean, for a lot of time. And this is a good point because we can tune T over Tc, so we can tune the temperature, and then we hope that we can extract alpha prime versus temperature, if any. And of course, just to say how translate so the alpha prime effects from linear to rotation, well, it's very simple because the radius of the orbit is alpha and the angular velocity is connected to alpha prime. Okay, that is obvious. Can we do this? Well, see, yes. You can see one vortex is pinned, the other one is rotating around. Okay? So then, of course, from this, you can see that if there is some dissipation, at the end you see that the vortex will collapse, and then you have the same sound wave propagating out from the center. So it's the same experiment, but just with one vortex dipole, and there is this motion instead of the linear motion. But you have to trust me that I can do this in a good way. So these are different orbits for different temperature, and I'm very proud of this because you can see at the level in which we can control T over Tf, that means T over Tc, okay, in the system. So we have very high sensitivity, and you can see how if I increase temperature, the orbit shrink faster. Okay, that makes sense because I expect mutual friction coefficient to be acting more at higher temperature. So the vortex start to move, the spiraling, but then alpha tends to bring them closer. And okay, these are details on how we fit the data. Well, I tell you, I have just put the graph with the graph of helium, okay? Our points are this with the error bar, and this is for alpha versus T over Tc, and this is, the red point will be always helium-4. The green point will be helium-3, and for the experiment we have both for linear than for this planetary motion. What I found interesting that alpha, and again, this is a phenomenological model, so it means that as soon as I know T over Tc, I can put my data on the helium ones. In fact, we don't have any other thing. So we took the data from the book of Carlo and Daniele, and from these papers that are these, and put our data. So our data suggests that for the alpha coefficient, superfluid Fermi gas at unitarity behaves like helium-4. Then we went to see alpha prime, and first thing that we found is that alpha prime is clearly non-zero. So there is an effect of this transverse mutual friction coefficient, and now it's bizarre because this is helium-4 that is 0, so fine, it's super small. For helium-3, absolutely is non-zero. Of course, change with temperature is increasing, and our data seems more or less moderately interested by temperature, but is clearly non-zero. Okay, and this is another parameter, but it's a combination between alpha prime and alpha, so that for the moment is related to the Reynolds numbers, but this is I don't want to talk about. Well, then we start the collaboration with Warsaw, and we run, and I'm not totally expert, actually at zero expert, so don't ask me too much detail, but what we know is that this is the only way that is known actually in the world, probably, in which is the only way in which people can simulate the dynamics of a strongly correlated Fermi system. It's still a mean field-like model, so I don't want to claim, but contains unbound state, contains pair breaking mechanism, contains fermionic nature. So just to give you the results, this is alpha versus T over Tc. These are the theory for two different dipole size. And unfortunately, we cannot fit is a bad word. We cannot simulate exactly for problem of the theory, the size of our dipole. But just to say anyway, the trend is captured. And we see, like expected and seen also by Nick and by Oxel's experiment, that the mutual friction coefficient alpha versus temperature increase. And it's nice to see that the theory catch the trend. Then also alpha prime. And okay, our data are scattered. We're trying to do better, even though it's difficult. But anyway, for sure we get more or less the fact that even in the theory, alpha prime should be different from 0. And I don't have the slide, but it's not, you have to trust me. This dependence depends strongly by the bound state population. Okay, from the theory, we can extract the number of bound states and the population, and we see that increasing temperature increase as alpha prime. Okay, so we are getting some intuition that this mutual friction coefficient can be really due to scattering of unwrapped state with the quasi-particle outside the Fermi superfluid. I have 1.57 minutes, so 1 minute and 53 seconds. So, and we change gear, but just to give you the idea of what is possible to do in this experiment, and we took the idea from Andrew paper, in fact. So what happens now if I take a superfluid and I put in one ring, I create a persistent current. I can do yes, and I will tell you very shortly how. But what happens if I create a system which I have two rings, one enclosed to the other, and I create the same persistent current but with the opposite sign, and then I remove the barrier that is in the center. So I create a counterflow, two persistent currents that are opposite in sign. So I don't have time, 0, but we can create our superfluid ring. And what we can do, okay, there are, of course, other people doing this. I apologize, but I just show you very fast, but there are people in Cambridge, and there are many places where you do. And what is possible to do with the DMD, we can phase imprint persistent current. And in fact, we demonstrate, and I don't have time, sorry for this, but I am here all the week, that we can create persistent current that must be quantized in unit of h over m. And this is the first step. For example, is 1, then you have 2. That is very similar to what happened in a superconducting ring in presence of a trapped flux. Okay, is the same thing. So we can phase imprint persistent current for different winding number, 1, 2, 3, h over m. And then we can detect using an interferometer way. So we have the way in which we can we create a sort of a quantum amperometer, taking the idea from the group of Bill Phillips and Jean Dalibard. We use the same way. And we can extract from the time of flight, from the spiral counting, how much current we put in the ring. Okay? Well, what happened now, and I'm done, if I remove, so I create +1, I'm done, and -1, and I remove this barrier. So this is V0 is the height of this barrier, and I decrease in time. So you see that the superfluids start to merge. And then you see that in the interference pattern, you start to see vortices appearing. And in fact, when I totally decrease the barrier, I create a vortex lattice with the number of vortices that is exactly twice the winding number modulus. Okay, this is for number of phase leakage or conservation of wave function, whatever you want to see, but is exactly what we expect. And of course, what we can do, we can create massive vortex lattice. These are probably 25. If we put +10, -10 winding. The point is that this system is not stable, as Henry was showing, and also Iacopo. And it's not stable because, in principle, what can happen is that the vortex start, this is the 0 time, to move in pairs, do a sort of ellipticity trajectory. And this, that you can see probably from the simulation also here. You can see that the vortex start to pile up like this, to pile up like this, to pile up like this. And this happens across the BC-BCS crossover, okay? And this, and I don't, now we stop. We see how fast the system loses this stability, and by using theory that are also related to classical, to GP, or to point vortex, we attribute to a rate to this departing from this crystallized motion. And we see that the rate seems to go close to the Kelvin-Helmholtz instability for the scaling, but not for the amplitude. Okay, so this goes like exactly V square, delta V square. But the amplitude of, so the velocity in which this happens seems to not match the classical, and even the GP =0 simulation. And with that, I don't have time, but I am here. I want to stop. And okay, and just, no, I just show you this. So what we want to do now, we are finishing up the measurement versus temperature, and then we are engineering vortex-phonon interaction, and we are going to have also the possibility to put impurity on the vortex dynamics to study impurity-driven transition in vortex matter. Thank you.
Questions?
Yes. Hi, Giacomo. Thanks for the nice talk. Before, if I remember correctly, you said that the size of the core is equal to the size of the mean free path. Is there a regime where the size of the mean free path is smaller than the size of the core?
Yes, okay. So in principle, if you go to move, so the mean free path is defined by, I cannot shrink. Less than this is not possible. But what I can do is to study BCS vortex, for which vortex core is becoming larger.
Okay, so because then if you have a finite temperature, so you have a fluid of excitation, you would imagine that the vortex would create some structure in the fluid. And for example, in a situation like that, if you had two same sign vortices which move, then the flow patterns might.
Well, I tell you, I did not have time to show, but if you want, what we see in the Kelvin-Helmholtz dynamics, that anyway, again, let's call Kelvin-Helmholtz, for me it's like, so is in fact the motion of vortex, no? That in fact happens. And in the BCS case, the reduction of the rate is even larger.
Yeah, go ahead.
I wanted to ask, are there, I mean, a lot of your analysis is based on using, for example, the Magnus force plus the dissipative force is equal to 0, which means that you're essentially assuming the vortex mass is negligible. So there's no inertia. Now, I'm just curious for these types of systems, is it possible to tune it such that the vortex mass is actually has a significant contribution, because that's something that hasn't really been explored much, and it would be interesting to understand it.
This is a good point. So for sure, in the case of point vortex model that we use, the mass is set to 0 arbitrarily. Okay, I want to say that there is a work now by the group of Pietro Massignani and Andrea Richaud. They add mass to the point vortex model, but this still become mathematics. And to tell you about the physics. So in fact, what can happen, but I cannot tell you the percentage, is that if you start to populate the under bound state, also connect to what was said by him, so the vortex are massive. So what we tried, but we have to try better, is that of course in this rotational of this planetary motion, we should see oscillation. So what I say, we are searching for that, because this will be an effective proof that the vortex, because of course you see another oscillation on top of one dynamics. I think I am positive, but it's difficult to see, because anyway, I think that the population of under state is still very small. What could be done, but not by me, is that if someone else, for example, we have a person here that can do in Raman Institute, if you have Bose-Bose mixture, and then you put the two superfluid and one of the two go to inside the other vortex, the vortex core generated only on the other species, then you will see. But with fermium, we have to rely to a population of understate that anyway has to follow the Fermi statistics. So I cannot put all the quasi-particle in one vortex, because it's a discrete level, and you know Fermi has to follow anyway Fermi distribution, and so they have to pile up in a specific way. But for Bose, you don't have this problem, so all the particles can fill up, given the geometry and the size of the vortex core.
Yeah.
So Giacomo, a curiosity, when you spin the system to get the instability, does the density profile change because of centrifugal force?
So we did not see this, but probably I must say that we did not take too much care. What I tell you is that probably we discussed, I don't know if with you or with Alessio in Trento, is that the phase imprinting technique is, maybe I did not explain what it is, but we just shine light pulse that has a gradient of intensity in a way that at the end is a azimuthal gradient. If you shine sufficiently short in time with respect to, okay, if you shine a light pulse on time scale that are shorter than this, actually should be, let's say, the perfect case would be much shorter than h bar over mu. Then you don't couple density, you just couple the phase, but it's not perfect. So, and you understand why it's not perfect, because I have to go from light to dark, and exactly in the region when it passes from light to dark, there is a region in which I can create excitation. So we don't know, I must say, if this density depletion that is following the phase imprinting, that actually is two, because it's one for the external, one for the internal, then there is the barrier. I don't know if this can create some transient at the beginning, since the Kelvin-Helmholtz or the instability rate happens to very short time scale. It's at the beginning. At long times, I don't have time, but we have clustering effect that with Alessandra we were discussing, and probably you also see in your experiment. So vortex start to cluster in big cluster. But I don't know if the transient is affected by this density depletion or imperfect phase imprinting. We should do the simulation using a real phase imprinting, also the GP. And probably we are going to run this.
But in the radial direction, there is deformation of the cloud.
We always see, I tell you, I did not check this, I can check this out. So we did not plot the aspect ratio. But actually we can discuss. If you think that is relevant, actually we can definitely do. It is just imaging analysis.
Try to find what can be the way out.
If you find, I will be happy.
And talk.
Thank you.
So it's kind of, at some point you show these vortices colliding, right? So in one case, they actually go together. In the other case, they suppose they annihilate and they create this wave. So is this the only way to transfer the energy from the incompressible to the compressible? And also you see this sort of line still, which is, I suppose, is a soliton line that is traveling.
Okay, this is actually, you mean this one?
Yes.
But this is we call a rarefaction pulse, but it's due only when we have that the two vortex dipole are in colliding at 120 degrees, and you see also in the theory by Luca. About the first question, I can tell you that I don't know the answer. So what we model is two regime in which we have dissipation due to mutual friction, like normal. Then the other one is the extreme case that is annihilation. That, by the way, you can see even with only one vortex. We just one vortex dipole. We don't need to have two pairs. I don't know. Actually, Luca can help in this, but I don't know if this is the only way in which you can transfer from the swirling to compressible. If I don't. So for sure, soliton, this will be very practically not stable in 2D. Actually, it's in 3D for the cloud. So that will be only stable in 1D. But then what actually was discussed with Iacopo, so you can have some transient, you could have sound wave, you can have some. So they call, now that you tell me, they call like, but this happens in the ring, solitonic, it's not solitonic ring. There are other topological mechanisms, but I don't know the answer to you if I never classify. For me, is the mutual friction or sound? But if you have another way, you have to tell me.
Thanks.
Since we seem to have a bit more time, any other questions? Maybe then I have one question. You see with the fermionic superfluids behavior which resembles, let's say, helium-4.
Mm-hmm.
Is there some intuitive understanding why you see it? Is it just that interactions are between spin up and spin down and not like in helium with the same spin, so well, it's a bit different?
To answer your question, so for sure, helium-3 is another beast. So the order parameter is very complicated and I will not. So about helium-4 and superfluid Fermi gas. So you know that there are many, so I don't, maybe I'm very qualitative, but just to give you one point. So the question is that the excitation spectrum, okay, from BC is collective, for go to BCS is single particle. But then if you are in the middle, you expect a sort of combination. And in fact, you have both for unitary Fermi gas. You can have pair breaking, but it's very, is inhibited because the gap is super large. So there are many properties for which the unitary gas behave more like a bosonic system than a fermionic system. So for me, in some way, could not be unexpected that in this property could be more similar to a bosonic system. And I don't want to enter about the symmetry of the gap of this order parameter. Maybe is the play a role. So I think that is just because of many other, also for critical velocity, also, you see that they start, in the unitary part, you clearly have sound very well defined. So in some way, I don't feel bad on that. I feel more, if you want, more confused by the fact that the helium-4 has a 0 alpha prime, and we clearly see do not. But I did not have time to show. There is a property of a Fermi superfluid, since you give me 1 minute more, that is very different. So that is sound diffusivity. And again, if I have just one picosecond, because I have the slide and I'm stopped with that. And this is why we are thinking about this Jordansky or this phonon interaction. And this, okay, this we can, this we discussed together. We can excite sound, but what I want to tell you is this. So sound diffusivity for unitary gas is constant, changing temperature. This was measured by Martinsville and MIT. It's specific of unitary gas because it's very strongly interacting. So there is no damping in the sound. So this means that it is possible that there is a mechanism that is due to sound that put our system closer to what the people see in helium-3, that are quasi-particle scattering. This case will be fully sound and eventually 100, but you see what I mean. So we are trying to understand which property can be connected to the behavior that we see closer to helium-3 than helium-4.